So thank you here for your interest. In 2016, I was in Texas A&M and I watched a nice presentation by Professor Vole Soboyeyo from Princeton. And he told this story. This is actually the question his mother made to him when he was explaining how he was developing nice blades to produce airplanes which were faster and would bring people faster to the place. And this reminds us why, in my opinion, we should do science. We have to improve the life of the people. So this is our social responsibility in science. In this case, what we are doing here, my student came with the idea to produce blends of PET and polyamide, nylon. His idea was to improve the barrier properties of the PET. The idea is to use PET for other kinds of films, not only for bottles. And of course, this has a social responsibility. It's related, sorry, going back here, but it seems that it goes only one direction. Now I see why. Okay. The reason for this is to save people from hunger. Because if you can preserve food better, you can help people to get fed. This is the idea of why we are doing this work. Of course, if we are doing a blend, we have to show it's compatible. And this is why I'm presenting this work today, to tell about the mechanical properties of this. Why PET? I don't need to remind you of all this. The important thing is that it is good for CO2 and not for oxygen. So it's not a good idea to place things that will get bad with time with PET. PA has a better performance in this, but has also biggest problems, and this is why we are doing blends. The idea is, of course, is it compatible? We had no idea before starting this. My student located which kind of PA resin he wanted to know. First one is a commercial resin, normal that we use every day. And the other one is this one here, which has a terephthalate group attached to the thing. The idea was that this terephthalate group would be better for compatibility. This is the production schedule. A samples are with the commercial PA resin, and B are with this modified PA. We did, of course, a DSC before the thing of the base resins to set the temperature of the processing. And here are the settings for the extruder that we use to produce the blends. One important thing is that this is homemade, so we couldn't control very good the final thickness of the films. They ended with many thicknesses depending on the batch. The kind of sample we did is a double and notched tensile test. simply because I wanted to do EWF, and they didn't want to do EWF. So they skipped it with 8 mm ligament length. They constructed a device to perform the test. And of course, this is the load displacement curve of a dent test, and to define the two quantities we are reporting here. And of course, also the integral of the curve is the work of fracture, which is specific if we divide by the ligament area. Here is the first result for the maximum load. Actually, it's a very good thing when we mix two polymers and nothing happens. It's a very bad thing to report this in a conference, because actually we see that there is almost no effect of PA on the strength of the film. A slight increase for this compatible resin, which is of course much more expensive than the commercial one, and a slight reduction for the commercial. The same happens with what we call the stretching stress. Also no visible differences. In the work of fracture, then we see an effect, and of course, if we mix too much PA, we pay with toughness. And finally, these are the conclusions. So we could produce the films. So there is almost no effect in the yield strength. There is also no big effect in drawing stress. The specific work of fracture decreased with the increase of PA, of course. And if we combine the two things, we could come with the conclusion that we shouldn't add more than 10% PA in this blend. Just to give an information for you, we did the barrier test, and this film is really better for barrier of oxygen. So thank you. This is